getting into solving for the pH of acids, both strong and weak. So the pH scale is dependent upon the concentration of the proton, the hydrogen ion, in the solution. It actually provides us a convenient way to represent the solution's acidity. So for the pH scale, it's a log scale based on 10, where the pH is equal to the negative log of the concentration of the H+. So for a solution where H+ is equal to 1 times 10 to the negative 7 molar, then the pH will be 7. The number of decimal places, just so that we know, for the significant figures is equal to the number of sig figs in the original number. So, for example, when you have H plus concentration is equal 1.0 times 10 to the negative 9, well, there is 2 sig figs in the 1.0, so that means we're going to have 2 decimals on our answer for the log. So that would be 9.00. Okay? This is a little tricky because it's completely out of left field and it's hard to understand. Similar other log scales that we can have, since we have OH, we can actually find the POH, where we take the negative log of the OH concentration. And it's also base 10. Because it's a pH of base 10, the pH changes by 1 for every power of 10 change in the H plus concentration. It's also important to know that when you add the pH and the POH together, you get 14. That will help us to solve out, okay? This picture is in your book on page 661 in case you want a closer look. Something I forgot to include in the notes are the antilogs. So what if I give you pH and I want you to solve for the H plus concentration? Well, use the antilog, and since it's base 10, the antilog will give you that H plus. So you take 10 to the negative pH to find the concentration of the H plus, and 10 to the negative POH to find the concentration of the OH, the hydroxide. So write these down. You're going to need them. If we were in lab, we can measure the pH of a solution, not the POH, but the pH, by using what's called a pH meter. And it's an electronic device with a probe that we can put into a solution. We also have pH paper, which is an estimate of the pH, but a pH probe or pH meter tells us the exact pH. And so that's why sometimes it's better to use. So let's go ahead and solve for the pH and the POH for each A and B. One thing I want to say before we start is that there's actually a lot of different options for solving these 4 equations, because using the 4 equations to solve for these. So I'm going to do it one way, but if you thought of doing it a different way, that's probably okay. So for A, we start out with the hydroxide concentration. So we can use that to find our POH. So I'm going to use the POH equals equation. So I'm going to take the negative log of the OH number. So that's 1.0 times 10 to the negative 3. Okay, when you take that negative log, if you're using my calculators, type in the number first, then hit log, and then hit the negative sign. Your answer is 3, but with our sig figs of logs, we have 2 sig figs in our concentration, so that means it's 2 decimal places, so 3.00. Well, that's the POH, that's part of it. Now we need the pH. So, to get the pH, I'm going to take 14, subtract the 3 from it, and that will give me my pH, because POH plus pH equals 14. So when I subtract, the pH is equal to 11. And we keep those 2 decimal places because when you add or subtract, you look at decimal places and both have 2. So there is a different path to find the same answer. So that's just what we did. So let's take a different route for B. Okay, so for B, we're starting out with 1 molar concentration OH. So instead of using the POH concentration, or POH equation, let's use our H plus times OH equals the 1.0 times 10 to the negative 14. The equation we learned just on level 62. So I don't know my H plus concentration, that's what I'm solving for, but I do know the OH, and that's 1. So when I divide over by the 1, that means that H plus is equal to, well, something divided by 1 is the same thing, 1.0 times 10 to the negative 14 molar. Okay, so I still need to find pH and POH. So I can now plug this number into my pH equation, negative log of 1.0 times 10 to the negative 14. Well, guess what? That is a total of 14.00, because we need 2 decimal places because of the 2 sig figs. So that's one of our answers. And then we can plug in our original, what we're given, for the POH. So the POH of the negative log of 1 is equal to 0. We also could have taken 14 minus 14 to figure out that POH is also 0. So, many different ways to solve. For example 5, the pH of a sample of human blood was measured to be 7.41 at 25 degrees Celsius. We need the POH, the H plus concentration, and the OH concentration for the sample. So, since I have the pH, I'm going to go ahead and subtract from 14 to get the POH. So the POH will be the 14 minus our 7.41. And when you subtract, you get 6.59. So that's one of our answers that we need. Then, to figure out the H plus and the OH minus, we can take the anti-log. So H plus will be easy because we already were given the pH. So that's 10 to the negative pH, so 10 to the negative 7.41. And use the 10 to the x button, don't use 10 caret. Use 10 to the x, it just makes life easier, okay? That equals 3.9 times 10 to the negative 8 molar. And for the OH concentration, I'm going to do the anti-log, but if you would like to do the KW expression we learned yesterday, or in level 52, that's fine. So 10 to the negative 6.59 equals 2.6 times 10 to the negative 7 molar. So that is our third. So we've been assuming that we were dealing with strong acids. Okay? So those calculations are fine for strong acids. We can look at their strong versus weak components. We could look at if it's fully dissociated or not completely broken up with the strong versus weak. But we can actually ignore some of the things because it's important to know that it's fully dissociated. So when you're looking at something, just make sure that you recognize what's in there, and it's important to write out the major species in the first step so that you can solve these problems correctly. Okay? Because sometimes you'll have a mixture or other things where it's not as clear cut. So when determining the pH of an acidic solution, the H plus comes from 2 places, the acid involved and from the dissociation of water. So you have to see which one's higher, for the water or for the strong acid. Well, for a strong acid, the position of water will be far to the left. So that means that the water won't break up. The acid will break up. So the amount of the H plus contributed by the water is negligible, so you don't need to include it. Okay, so thinking about that, we're still going to be able to do things about the same way. Okay, so for A, we want to calculate the pH. We're just given a whole entire compound, right? And these are both strong acids. So for A, we know that if we have our strong acid, nitric acid, the HNO3, dissociate, that's going to break up into H plus and the nitrate ion. Okay? Well, it also really does contain, it's going to contain these 2 things, and it's also going to contain the water, because the water is not going to break up. Well, because the water is not breaking up, almost all of the H plus comes from the breakdown of the acid, so we're going to use the concentration given for the acid equal to the concentration of the H plus. So we're just going to use our 0.10 molar is equal to the H plus concentration. Okay, so then now we can go ahead and solve for pH. So the pH is equal to the negative log of 0.1, and so that is equal to 1.00. So for part B, this time, hopefully you split your page in half. It is a strong acid, so it will be broken down into, it's going to go from HCl into the H plus and the Cl minus, so those will be present, right? And then water will also be present, but it's not going to break up because it's not favored. But looking at the number here, it's times 10 to the negative 10. A negative 10 means it's a really tiny decimal. And so because it's so tiny, the concentration that we're given actually won't have an effect on the pH. So the pH will stay the same as pure water. And the pH of pure water is 7.00. So on this one, we kind of have to look at it and say, okay, there's hardly any acid being put into the water whatsoever to make the solution. So if there's not very much acid, that means that the pH will be more towards the water, normal pure water, which is 7, and neutral. To calculate the pH of weak acids is a little bit more complicated. We have to use equilibrium expressions and the quadratic formula sometimes, but maybe we'll be able to do the assumption rule, okay? So here are the steps. They're listed for you. I'm not going to say anything. But the most important thing is you have to choose the species that can produce, number 2, and write the balanced equations so that you know which one to use. So you can write your K expression, okay? So that tells us how we are going to be able to figure out and where do we plug things into our K expressions. The hypochlorite ion is a strong oxidizing agent often found in the household bleaches and disinfectants, and it forms hypochlorous acid, which is OHCl, and it has a Ka value of 3.5 times 10 to the negative 8. We need to know the pH of a 0.100 molar solution of the hypochlorous acid. Okay, well, so in our solution, it contains both our acid and it's aqueous, so that means it also includes the water. So, to know which one is getting broken up to be acting like the acid, we have to look at their Ka versus the Kw. Okay, so this is our Ka given in the problem, and Kw is what we learned about in 62, and that's the 1.0 times 10 to the negative 14. Okay, well, we're comparing the exponents on the 10 right now. So negative 8 versus negative 14. Ka is significantly greater than, that's what the double greater than sign means, significantly greater than the Kw because it's negative 8 versus negative 14. That's a lot of decimal places. So we're just going to use the Ka, so that means we're just going to use the hypochlorous acid to help us figure this out. Okay, so let's go ahead and write out the equation for when the hypochlorous acid breaks down. So we have the acid, and we take out the proton, the H plus, and then what's left over is the conjugate base, and so that is the OCl minus, okay? And now, to write our K expression, let's go ahead and do that. Ka is equal to products over reactants, just like we did in chapter 13. So we have H plus times the OCl minus all over the concentration of the acid. Okay, next up, we need to do our ice chart. So initially, we have 0.100 molar of the acid, and we don't have any of the ions present. The change will be negative x because we need to go towards the side with the zeros, and then positive x for the products because we're going towards it. We're gaining on that side. So at equilibrium, it'll be 0.100 minus x, and then x and x for the top. Okay, so on this, we're going to make our assumption because we're dealing with very small numbers because we have this really small Ka. Okay, so I'm going to plug it in as if I'm already assuming. So we have 3.5, this is our Ka given in the problem, times 10 to the negative 8 equals, it's x times x, so I'm just going to go ahead and put x squared over. And so on your assumptions, remember you take off anything that's added or subtracted x. So in the bottom, we would have 0.1 minus x. So I'm just going to take off the minus x, and I'm going to leave the 0.1. Okay? So now you got to do a little algebra, and you multiply it over the 0.1, and then square root that side to figure out that x is equal to 5.9 times 10 to the negative 5. Well, that is the concentration of both the H plus and the OCl minus. So that tells us that is the H plus right there. Well, guess what? Now we can solve for pH, which is what we were trying to find. So the pH equals the negative log of our 5.9 times 10 to the negative 5. So the pH is 4.2 purity. If you were to check the assumption, it does work because the answer, the 5.9 times 10 to the negative 5 for x, is 0.059% of the original concentration. So I think we're okay. Sometimes you can have a mixture of weak acids. And so when it contains two weak acids of very different strengths, we're going to actually follow the same steps as in example 7 and see which one would be the most stronger and then use that one only. We need to know the pH of a solution that contains 1 molar hydrocyanic acid who has a Ka of 6.2 times 10 to the negative 10. And we're comparing that to a 5 molar nitrous acid that has a Ka of 4.0 times 10 to the negative 4. Well, it's an aqueous solution, so we also have to think about water being involved in there. And water, we use the Kw, 1.0 times 10 to the negative 14 with the comparison. Well, looking at these three numbers, we have times 10 to the negative 10 to the negative 4 and to the negative 14. Negative 4 is the big number out of these three. So, because negative 4 is the big number, that means that we are going to use specifically the nitrous acid as our way of figuring out the H plus concentration, just like we did in our last example. Okay, so we can go ahead and write out our dissociation reaction for that, where it breaks down and you get rid of one proton and you're left over with everything else, which is nitrite. And our Ka expression is going to be products of reactants. So H plus times the nitrite all over the nitrous acid. And let's go ahead with our ice chart. Okay, so our initial concentration is given to us as 5 molar of the acid, and we don't have any of the ions yet. So we're going to lose the acid and we're going to gain the ions. So equilibrium, it's 5 minus x, and then x and x. Again, we're times 10 to the negative 4, which is pretty small. So we are going to assume that we can leave off the added subtracted x. Okay? So to set up our K expression to solve, we have 4.0 times 10 to the negative 4 equals, it's x times x, so x squared, over just the 5, because we're assuming that we don't need the rest. All right, with our algebra, to solve x is equal to 4.5 times 10 to the negative 2. If you check the assumption, it's 0.9% of the original, so we are still good. And that is equal to x, which is our H plus concentration. So the problem wanted the pH, so now we can go ahead and plug into our pH equation again. Negative log of 4.5 times 10 to the negative 2, and that is equal to 1.35. So as long as you look at all of the Ka or Kws possible present in the solution mixture, pick the right one, and then it's not too bad. Last but not least, we have this percent dissociation equation. The exact amount of weak acid that has dissociated in achieving equilibrium can be determined by the percent dissociation method using this equation. Really, it's almost exactly the same as doing the assumption, where you take the amount dissociated, so the X that you solve for, over the initial concentration of your acid, your reactant, and then multiply by 100. So your unit is going to be a percent sign. For a given weak acid, the percent dissociation increases as the acid becomes more dilute, just so you know. So let's calculate out that percent dissociation. If we have acetic acid, which has a Ka of 1.8 times 10 to the negative 5, and a solution of 0.1 molar acid. So we have the acid, which has a Ka of 1.8 times 10 to the negative 5, versus it's also an aqueous solution, so it has water, which has the Kw, and that is still really tiny, so we can assume that the water does not donate to the H plus concentration, just like we were doing previously. So for our reaction, we have the acetic acid breaking down into H plus and acetate, and our K expression for Ka equals the H plus times the acetate all over the acetic acid So for our ice chart, we have our molarity is 0.1, and we don't start with the ions. We're losing acid, gaining ions. So at equilibrium, there we go. All right, so we got to solve for H plus now. Well, or X technically, which is the H plus. So we're going to solve for it because Ka is so tiny and we have 0.1. We're going to assume that the X is going to be very small and not have an effect, so we will do the assumption. So then we have 1.8 times 10 to the negative 5 equals X times X, so X squared, over 0.1, leaving off the minus X. So then when you solve for X, X is 1.3 times 10 to the negative 3. And this technically, since it is H plus, is the unit could be on their molarity, molar, okay? So now to find the percent dissociation, we are going to take our X that we solved for, divided by the initial concentration, so, and multiply by 100. And when you do that, you get 1.3%. So this is telling you that only 1.3% of the acid actually breaks down into the H plus concentration. The rest of it stays put together. That's why it's called a weak acid, because it doesn't break up very well. In case you need any more help with these solving acid-based problems, there is more information on pages 674 and 675 in your textbook. There's actually a list of steps for you to use. But if you don't want to look at it, that is okay too. So the problems for this level are number 52, 56, 63, 74 AB, and 75.
First things first, I'm the realest.